Hey everyone, and welcome to this MasterClass Explainer. We're going to dive right into the source material today to level up our chemistry game together, moving all the way from foundational concepts straight into those JEE and NEET Advanced boss battles. If you've ever felt like the periodic table is just this chaotic grid of random numbers and exceptions, well, today is the day that completely changes. We're going to decode the hidden laws that govern exactly how elements interact, bond, and break apart.
Here is our game plan for today. We're covering 4 main areas. 1. The core foundation. 2. ISC board extras. 3. The JEE and NEET Masterclass. And 4. Free resources and next steps. We'll build this up step by step, starting with the CBSE core, pushing into those tricky ISC solubility rules, and finally cracking the advanced formula conversions and inert pair effects. Let's get right into it. Kicking things off with Section 1, Core Foundation, focusing on periodic trends and electronegativity. Let's see how elements fundamentally behave across the board. Right off the bat, there's a really interesting distinction here between two concepts that constantly trip students up: electronegativity and electron gain enthalpy. Think of electronegativity like a literal tug-of-war in a relationship. It's an atom's tendency to pull shared electrons toward itself when it's already locked in a chemical bond. It's not a physically measurable energy, it's just a relative tendency. Electron gain enthalpy, on the flip side, is the actual measurable energy released or absorbed when an isolated gaseous atom captures an entirely new electron. So one is about sharing and the other is about absolute capture. Now, to measure that tug-of-war, we rely on the Pauling scale. You absolutely need to memorize these Pauling scale numbers. Consider them your essential exam toolkit. Fluorine is the undisputed king here at a perfectly assigned 4.0. Oxygen sits right behind it at 3.5, while nitrogen and chlorine are tied at 3.0. Whenever you're trying to figure out which way a bond is polarized, you just look at these numbers. The atom with the higher number wins the electron tug-of-war every single time.
And as you'll see here, electronegativity generally increases from left to right across a period, and it decreases as you move down a group. Why does it do that? Well, it all basically comes down to atomic radius and effective nuclear charge. As you move across a period, the nucleus is packing in more protons, which pulls the electron cloud closer and cranks up that electronegative pull. But as you go down a group, you're adding entire new electron shells. The atomic radius gets larger, so those outer electrons are way further from the nucleus, meaning the atom's ability to attract shared electrons really drops off.
What this ultimately means is that maximum chemical reactivity sits at the extreme left and the extreme right of the periodic table, which leaves the center relatively calm. On the extreme left, you've got the alkali metals with super low ionization enthalpies. They desperately want to lose electrons and become cations. When they react with oxygen, they form strongly basic oxides like sodium oxide. Over on the extreme right, halogens are the exact opposite. They desperately want to gain electrons, they form anions, and their oxides, like dichlorine heptoxide, are incredibly acidic. It really is a perfect spectrum of behavior.
Moving right along to Section 2, ISC Board Extras, we are diving into the Battle of Solubilities, which is a specialized application that catches a lot of students off guard.
Have you ever wondered why certain salts completely vanish into water in an instant, while others, like barium sulfate, just stubbornly sit at the bottom of the beaker like sand? Trust me, it's not random. There is a very specific thermodynamic battle happening down at the microscopic level. So, the crucial takeaway is that solubility is a literal battle between two incredibly powerful forces: hydration enthalpy and lattice enthalpy. Lattice enthalpy is the energy locking those positive and negative ions together in their solid crystal grid. Hydration enthalpy, on the other hand, is the energy released when water molecules surround and try to yank those ions apart. For a salt to actually dissolve, the hydration enthalpy, pulling the ions into the water, simply must overpower the lattice enthalpy, holding them together.
Let's see how this builds into an actual exam question using group 2 sulfates. As you move down the group from beryllium to barium, and this works for group 1 carbonates too, by the way, solubility just plummets. Why? Well, for group 2 sulfates, because the sulfate anion is absolutely huge, the lattice energy of the crystal barely changes at all as you move down the group. But as the metal cation gets larger, going from a tiny beryllium ion to a massive barium ion, its charge density drops, meaning its hydration enthalpy decreases rapidly. Since the water's pull gets weaker, but the crystal strength stays pretty much the same, barium sulfate ends up being completely insoluble. All right, we've made it to Section 3, the JEE and NEET Masterclass. This is the boss stage where we're going to get a bit more mathematical and theoretical with advanced formulas, diagonal, and inert effects.
We talked about the Pauling scale earlier, but digging into the source material, there's also the Mulliken scale, which simply averages an atom's ionization energy and its electron affinity. To convert that Mulliken scale over to the Pauling scale, you just divide it by 2.8. And this gives us a massive, high-yield shortcut formula for your exams. Pauling electronegativity equals ionization energy plus electron affinity, all divided by 5.6. Just keep in mind, this specific formula expects those energy values to be in electron volts.
Next up, we absolutely need to define ionic potential, which we denote with the Greek letter phi. This is basically a measure of charge density. You calculate it by taking the charge of a cation and dividing it by the square of its radius. This one single ratio is actually the secret key to unlocking one of the strangest quirks of the entire periodic table.
And that mathematical relationship is exactly why diagonal relationships exist. Have you ever noticed that lithium acts a whole lot like magnesium and beryllium acts remarkably like aluminum, even though they're in completely different groups and periods? Here's why. As you move across a period, charge goes up and size goes down, driving the ionic potential way up. But as you move down a group, size increases, which drives ionic potential down. So if you move diagonally, one step right and one step down, those two effects literally cancel each other out. This mathematically proves why these specific pairs share almost identical chemical behaviors.
Let's look at the hard evidence for beryllium and aluminum. Because they have that matching ionic potential, they are basically chemical twins. They both form amphoteric oxides, which means their oxides can react as both acids and bases. They both construct polymeric covalent chlorides rather than your standard simple ionic ones. And honestly, this is the coolest part. Both metals passivate, meaning they become totally unreactive when you drop them into concentrated nitric acid because they instantly form this tough, protective oxide layer on their surface.
Moving even deeper into advanced territory, we hit the inert pair effect. You're going to see this in the heavy p block elements way down at the bottom of the periodic table. The poor shielding effect provided by those diffuse 4f and 5d inner orbitals completely fails to block out the massive nuclear charge. Because of that, the nucleus pulls so insanely strongly on the valence s electrons that they become inert. They are held way too tightly to the nucleus to actually participate in any chemical bonding. And this perfectly explains why for heavyweight elements like thallium, lead, and bismuth, their lower oxidation states are actually vastly more stable than their higher ones. For example, lead usually forms a +4 charge based on its group, right? But because of the inert pair effect locking away those two s electrons, lead 2+ is vastly more stable. In fact, if you actually manage to create a lead 4+ compound in a lab, it's going to act as a violently strong oxidizing agent, just desperately trying to steal electrons to get back down to that super stable 2+ state.
Finally, Section 4, Free Resources and Next Steps. We have covered some serious ground today, from foundational trends to complex ionic potentials and quantum shielding. But how do we lock this in for test day?
The absolute best next step for you right now is to subscribe to the MasterClass 11 and 12 channel on YouTube. And whatever you do, don't forget to click the Telegram link in the description below to join our community and download your free notes and practice worksheets today. Mastering all these rules definitely takes practice, but once you start seeing the underlying matrix of the periodic table, you really can't unsee it. Which leaves us with one final crazy thought. If charge density and electronegativity so perfectly dictate everything we observe today, what exactly happens to these rules when we synthesize entirely new, super heavy elements, where relativistic effects take over completely? It is definitely something fascinating to think about. Keep studying hard, and we'll see you in the next explainer.